Welcome! In this session, we'll tackle LeetCode problem number 137, titled Single Number 2. This is a fascinating problem that involves finding the unique element in an array where every other element appears exactly 3 times. Let's dive in and explore the solution step by step. In this problem, we are given an array of integers called nums. Each number in this array appears exactly 3 times, except for one unique number that appears only once. Our task is to find that single number that occurs exactly once. Importantly, we need to achieve this with a solution that has a linear time complexity, denoted as O(n), meaning we can only loop through the array once. Additionally, we are constrained to use constant extra space, which means the memory usage of our solution should not depend on the size of the input array. The input array, nums, does not come in any specific order, and it is guaranteed that all numbers but one appear 3 times. The output should simply be the single integer that only appears once in the array. Now let's look at some examples to understand the problem better. For the input array nums equals 2, 2, 3, 2, the number 2 appears 3 times, while the number 3 appears exactly once. Hence, the output is 3, as it is the only number that does not repeat 3 times. Similarly, for the input nums equals 0, 1, 0, 1, 0, 1, 99, we see that the numbers 0 and 1 each occur 3 times. The number 99, on the other hand, appears only once, making it the result of this example. For another example, consider the input nums equals -2, -2, -2, -3. Here, the number -2 appears 3 times, while the number -3 appears just once. Therefore, the output is -3. These examples demonstrate the consistent pattern that all numbers except 1 occur exactly 3 times, and our goal is to isolate the single number that breaks this pattern. Now, let's review the constraints and edge cases to ensure our solution is robust. The array nums will have a length between 1 and 3 *10^4. Each element in the array will be an integer within the range of -2^31 to 2^31. Crucially, every number in nums appears exactly 3 times except for 1, which appears exactly once. For edge cases, if the array has only one element, such as nums equals 42, then that single number is the output. Arrays with all negative numbers, such as nums equals -1, -1, -1, -99, must still return the correct result, which in this case is -99. For large input sizes near the upper limit, the solution must remain efficient and operate in O(n) time. Additionally, the array can contain a mix of positive and negative integers. For example, in nums equals -1, 1, -1, -1, 1, 1, 7, the numbers -1 and 1 each appear 3 times, while the number 7 appears only once. The output in this case is 7. These examples and constraints highlight the importance of designing an efficient algorithm that can handle a wide variety of scenarios while satisfying the problem's requirements for time and space complexity. To solve the problem of finding the single number that appears only once while all other numbers appear exactly 3 times, we can start by exploring some intuitive approaches. The brute force method involves using a frequency count. Here, we iterate through the array and count the occurrences of each number using a hash map. Once we have the frequencies, we identify the number that occurs exactly once. While this method is simple and runs in linear time, O(n), it requires additional space for the hash map, which violates the constraint of constant extra space. Another option is the sorting approach. By sorting the array, we can group numbers that appear 3 times together. The single number will stand out as the one that does not fit the pattern. This method reduces space complexity to O(1) if sorting is done in place, but it increases time complexity to O(n) log n due to the sorting step, which violates the linear time constraint. Now, a more efficient approach leverages bitwise manipulation. This method is based on the observation that since every number except 1 appears 3 times, the bits of the numbers can be tracked modulo 3. By using 2-bit masks, 1s and 2s, we can track how many times each bit has been set across all the numbers. For each number in the array, we update these masks to reflect whether a bit has been seen once, twice, or 3 times. After processing all the numbers, the 1's mask will hold the bits of the single number, while bits appearing 3 times will have been cleared. This approach is not only intuitive but also meets the constraints of linear time complexity, O(n), and constant space complexity, O1, making it a strong candidate for the optimal solution. The core idea behind the bitwise manipulation approach lies in treating each bit of the numbers independently. If a bit appears 3 times across different numbers, modulo 3 arithmetic ensures that it is reset to 0. This allows us to systematically clear bits that appear 3 times while retaining the bits of the number that appears only once. The result is a highly efficient solution with a time complexity of O(n), as it requires only a single pass through the array, and a space complexity of O(1), as it uses only 2 integer variables, 1s and 2s. These properties make bitwise manipulation the optimal strategy for solving this problem. Compared to the brute force approach, it eliminates the need for an auxiliary data structure like a hash map, reducing space usage. It also outperforms the sorting approach by avoiding the costly O(n log n) sorting step, maintaining a linear runtime. Here is the Python implementation of the bitwise manipulation approach. The function single number initializes 2 variables, 1s and 2s, both set to 0. These variables track the bits that have appeared once and twice, respectively. For each number in the input array, we update 1s and 2s using bitwise operations. Specifically, the XOR operation adds the current number's bits to the respective mask, while the AND operation with the complement ensures that bits appearing 3 times are cleared. This process systematically filters out bits that appear 3 times, leaving only the bits of the number that appears once in the ones variable. At the end of the loop, ones contains the result, which is returned. This implementation is both concise and efficient, achieving the optimal performance required by the problem constraints. The problem we're tackling here is to find the unique number in an array where every other number appears multiple times, for example, twice. Our goal is to solve this efficiently, avoiding unnecessary computational overhead. One approach is the brute force method, where we count the frequency of each number in the array. Here's how it works. First, we initialize an empty dictionary to store the frequency of each number. As we iterate through the array, we update the count for each number in this dictionary. Finally, we traverse the dictionary to find the number that has a frequency of exactly 1 and return it. While this approach is straightforward and works in O(n) time for traversing the array, it requires additional space proportional to the size of the input, specifically O(n), to store the frequency counts. Now, we move to a more optimized approach that leverages the XOR operation. XOR, or exclusive OR, has some unique properties that make it especially useful here. First, a number XOR'd with itself results in 0. Second, a number XOR'd with 0 remains unchanged. Third, the operation is both commutative and associative, meaning the order in which we apply it doesn't matter. By using these properties, we can efficiently cancel out the numbers that appear twice, leaving only the unique number. To implement this, we initialize a variable called result to 0. As we iterate through the array, we compute the XOR of result with each number in the array. Once the loop is complete, result will contain the unique number. This method eliminates the need for additional data structures and operates in O(n) time with O(1) space. Let's break down why XOR works so effectively here. When a number appears twice in the array, XORing it with itself yields 0, effectively canceling it out. The unique number, however, remains unaffected because XORing it with 0 doesn't change its value. This makes XOR a perfect fit for this problem as it allows us to isolate the unique number. The efficiency of this approach stands out as it requires only one traversal of the array, making it O(n) in time complexity. Additionally, it uses no extra space beyond a single variable, resulting in O(1) space complexity. When handling edge cases, such as an empty array, we should return an error or handle it appropriately. If the array contains only one element, that element is the unique number. This method is also scalable, efficiently handling large input sizes. To compare the data structures used in these approaches, the brute force method relies on a dictionary to store the frequency counts of numbers. While this is simple to implement, it uses O(n) space, which can become a limitation for larger inputs. On the other hand, the optimized XOR approach uses a single variable to store the result, achieving O(1) space complexity. The final optimized algorithm can be summarized as follows. Given an input array of integers where every number except 1 appears twice, our task is to find the unique number. We start by initializing a variable, result, to 0. Then, we iterate through the array, updating result by XORing it with each number. Once the iteration is complete, result will contain the unique number, which we then return. Let's walk through an example to see the XOR approach in action. Consider the input array 4, 1, 2, 1, 2. We initialize result to 0. The first number is 4, so we compute 0 XOR 4, which equals 4. Next, we XOR 4 with 1, resulting in 5. Then, 5 XOR 2 gives 7. Continuing, 7 XOR 1 results in 6. Finally, 6 XOR 2 gives 4. After processing all the numbers, result holds the value 4, which is the unique number in the array. This example demonstrates how the XOR operation efficiently isolates the unique number. The time complexity here is O(n), as we traverse the array once, and the space complexity is O(1), as no additional data structures are used. This code solves LeetCode problem 137, single number 2, using a highly efficient bitwise manipulation technique. The goal is to find the single number in an array where every other number appears exactly 3 times. Explanation. 1. Initialization. We define two variables, 1s and 2s, initialized to 0. These variables will track the bits that appear once and twice, respectively. 2. Iterating through the array. For each number in the input array nums, we update 1s and 2s based on the following logic. 1s equals 1's caret number, and 2s, this updates 1s to include bits that have appeared exactly once. The 2s ensures bits that have already appeared twice are excluded from 1s. 2s equals 2's caret number, and 1s, similarly, this updates 2s to include bits that have appeared exactly twice, while excluding bits that have already transitioned into 1s. 3. Final result. After processing all numbers, 1s will contain the bits representing the number that appeared exactly once in the array. This is because any bit that appeared 3 times will be cleared out of both 1s and 2s. 4. Return the result. Finally, we return 1s, which holds the single number. Efficiency. Time complexity. The solution runs in O(n), where n is the size of the input array. Each number is processed exactly once. Space complexity. The solution uses O(1) additional space, as we only use 2 variables, 1s and 2s, to track the state. Edge cases. If the array contains only one number, that number will be returned correctly. If the array has negative numbers or 0, the bitwise operations will still handle them correctly. This solution is optimal and avoids the overhead of additional data structures like hash maps or counting arrays, making it both memory efficient and fast for large inputs. This is the Java implementation of the solution for LeetCode problem number 137, single number 2. The code uses 2 integer variables, 1s and 2s, to track the bits appearing once and twice, respectively. The logic is implemented using bitwise operators to efficiently determine the single number that appears exactly once in the input array. Key differences from the Python implementation include explicit type declarations and the use of Java's enhanced for loop syntax for iterating over the array. The solution runs in O(n), time with O(1) space complexity, making it highly efficient. To solve this problem, we use 2 variables, 1s and 2s, which help us track the bits that have appeared exactly once and twice, respectively. Initially, both 1s and 2s are set to 0. Then, as we iterate through the input array, we update these variables based on the current number. For the first number, 2, we calculate 1s as 1's caret number, and 2s, which evaluates to 2, and 2s as 2's caret number, and 1s, which remains 0. After the first iteration, the state of our variables is 1s equals 2 and 2s equals 0. On the second iteration, with the same number, 2, we update 1s to 0 and 2s to 2. This change reflects that the number 2 has now been seen twice. For the next number, 3, we update 1s to 1 and 2s back to 0, indicating that 3 has been seen once. Finally, when processing another 2, 1s becomes 3, and 2s remains 0. The value of 1s at the end, which is 3, represents the single number that appears exactly once in the array. Now we move to the second example with the input array 0, 1, 0, 1, 0, 1, 99. Again, we initialize 1s and 2s to 0. For the first number, 0, both 1s and 2s remain unchanged at 0. When we process the next number, 1, 1s becomes 1 while 2 stays 0, indicating that 1 has been seen once. The following number, 0, doesn't change the values of 1s and 2s. When we encounter 1 again, 1s is updated to 0, and 2s becomes 1, showing that 1 has now been seen twice. For the next 0, 1 stays 0, and 2s remains 1. Another 1 resets both 1s and 2s to 0, as this is the third occurrence of 1. Finally, when we reach the last number, 99, 1s becomes 99, and 2 stays at 0. This means the single number in this array is 99. In this example, we see how the repeated updates to 1s and 2s allow us to filter out numbers that appear exactly 3 times. For instance, as we iterate through the array, each occurrence of 1 toggles the bits in 1s and 2s appropriately. After the third occurrence, both 1s and 2s reset to 0, effectively removing 1 from the state. When we process 99, which appears only once, the bitwise operations ensure that it remains in 1s and does not interact with 2s. This approach showcases how the algorithm uses these two variables to isolate the single number amidst multiple duplicates. In the third example, we analyze the input 1, 1, 1, 4. Starting with 1s and 2s at 0, the first number, 1, updates 1s to 1 while 2 stays at 0. The second occurrence of 1 resets 1s to 0 and updates 2s to 1, reflecting that 1 has been seen twice. The third occurrence of 1 resets both 1s and 2s to 0, as it has now been seen 3 times. Finally, when the number 4 is processed, 1s becomes 4, and 2s remains 0. The value of 1s, which is 4, is our result, as it represents the single number that appears exactly once in the array. This example further demonstrates the power of the bitwise approach. By continuously updating 1s and 2s, the algorithm can efficiently remove numbers that appear 3 times while retaining the number that appears only once. Each bitwise operation ensures that the state of 1s and 2s reflects the exact count of appearances for each number, modulo 3. At the end of the process, the value in 1s gives us the single number we're looking for, which, in this case, is 4. In this solution, the time complexity is O(n), where n represents the size of the input array, nums. This is because the algorithm processes each element in the array exactly once. It achieves this through a single loop that iterates over all elements. Within the loop, we perform bitwise operations like XOR, and NOT. These operations are highly efficient and execute in constant time, or O(1). Therefore, combining the n iterations of the loop with the O(1) operations performed in each iteration, the overall time complexity is O(n). Now, looking at space complexity, the solution is highly optimized. It uses only 2 integer variables, 1s and 2s, to keep track of bits that appear once and twice, respectively. These variables occupy a fixed amount of memory, regardless of the size of the input. Furthermore, no additional data structures or dynamic memory allocation are used. This means the space complexity is constant, or O(1), making the algorithm both space-efficient and scalable. When analyzing the algorithm's performance across different scenarios, we see that the time complexity remains O(n) in the best, average, and worst cases. This consistency arises because the algorithm always iterates through the entire array, regardless of how the input is distributed or structured. Similarly, the space complexity is O(1) in all cases since the number of variables used does not change with the input size. If we compare this to a brute force approach, a common method might involve using a dictionary or hash map to count the frequency of each number. While the brute force method also achieves O(n) time complexity for iterating through the array, it incurs an additional space complexity of O(n) to store the frequency counts. By contrast, the current solution eliminates the need for extra memory by leveraging bitwise operations to track occurrences at the bit level. This optimization reduces space complexity to O(1) while still maintaining the O(n) time complexity, making it more efficient overall. To mathematically verify the time complexity, consider an array of size n. The algorithm runs a single loop that iterates exactly n times. Within each iteration, it performs a fixed number of bitwise operations XOR, and NOT, which are all constant time operations, or O(1). Since the total number of operations is directly proportional to n, the overall time complexity is O(n). When we analyze space complexity mathematically, the algorithm's memory usage is determined by the two integer variables, 1s and 2s. These variables occupy a constant amount of space, regardless of the input size. The solution does not perform dynamic memory allocation or use additional data structures, ensuring that the space complexity remains O(1). In summary, the solution achieves O(n) time complexity and O(1) space complexity, which is optimal. This efficiency makes it a clear improvement over brute force methods, both in terms of runtime and memory usage. When solving this problem, there are several common mistakes to watch out for. First, not considering edge cases can lead to runtime errors. For example, if the input array contains just one element, like 1, your logic must correctly identify it as the unique number. Similarly, forgetting to handle empty arrays could cause unexpected behavior. Another frequent mistake involves incorrect hash map updates. If you're using a hash map to count frequencies, make sure to initialize and update the map correctly, or your frequency counts may end up inaccurate. Additionally, some solutions overlook the possibility of negative numbers. While the problem might seem to involve only positive integers, the input can include negative values, so your solution needs to handle them properly. Finally, over-relying on sorting can be inefficient. Sorting the array to find the unique number works, but it increases time complexity to O(n) log n, which isn't optimal when O(n) solutions are available, such as those using XOR or hash maps. Now, let's talk about memory considerations and interview expectations. When using a hash map, it's important to be mindful of memory limits. The space complexity of a hash map is O(n), so if the input size is extremely large, this approach could exceed memory constraints. In such cases, alternatives like the XOR approach are more efficient since they reduce space complexity to O(1). Speaking of XOR, it's a technique that's particularly useful in these types of problems. The XOR operation has unique properties. XORing a number with itself cancels it out, and XORing with 0 leaves the number unchanged. These properties make it possible to solve the problem in O(n) time and O(1) space. Interviewers often expect you to discuss trade-offs between approaches. While hash maps are straightforward, XOR is optimal in terms of both time and space complexity, so it's a good idea to highlight these differences. Additionally, always clarify assumptions during an interview. For example, confirm whether there's exactly one unique number or if the input might include multiple unique numbers. This ensures your solution aligns with the problem's constraints. There are also related problems worth exploring, as they often share similar patterns. For instance, in LeetCode 136, the goal is to find the number that appears only once when all others appear twice. LeetCode 137, which we're discussing here, extends this to finding the number that appears once when all others appear 3 times. LeetCode 260 takes it further by asking you to find two numbers that appear only once when all others appear twice. Another example is LeetCode 287, where you need to identify the duplicate number in an array with elements ranging from 1 to n. In terms of alternative approaches, the hash map approach is a solid choice for this problem. It offers a time complexity of O(n) and is simple to implement, but it does use extra memory due to its O(n) space complexity. On the other hand, the XOR approach is both time and space optimal, with O(n) time and O(1) space complexity. However, it requires a good understanding of XOR properties, which might not be immediately intuitive for everyone. Lastly, let's consider the sorting approach. This method has a time complexity of O(n) log n, which is slower than the hash map or XOR-based methods. On the positive side, its space complexity is O(1) if in-place sorting is used. While sorting can work for this problem, it's not as efficient as the other methods we've discussed. It's worth noting that sorting modifies the original array, which might not always be acceptable depending on the problem's constraints. Overall, while this approach is valid, it's generally better to aim for the more optimal solutions like XOR or hash maps, especially in scenarios where performance matters or memory usage is a concern. Great job making it to the end. To recap, we reviewed a brute force approach to solve this unique number problem and highlighted key takeaways. Keep practicing problems like this to enhance your coding skills, and don't forget to subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!